Okay, so here we go, picking up where we left off last time. So we were talking about the equation of a plane in 3 space, and I want to point out a neat little trick to keep on the lookout for. This comes up surprisingly often, I think, and that is if there are no y's in your equation of your plane. So notice here, for example, there are 0 y's in this equation. Right? So when that happens, you get a powerful geometric conclusion, and that is that the plane is parallel to the y-axis. So before I explain why this works, let me just point out how valuable this theorem is. You don't have to do a bunch of algebraic effort to get the payoff. Just glance at the equation. If the coefficient of y's is 0, or more likely, if that term just isn't there in the equation of the plane, I mean, it's available at a glance, right? Again, you don't have to put in a bunch of effort to find it. And then for that practically 0 effort, you get a significant geometric conclusion about what your plane is parallel to already, just at a snap. So I think it's a lovely little result. Here's one point of view on why this is true. Keep in mind that when you look at the equation of a plane, the coefficients in the equation of the plane immediately tell you your normal vector. Right? So we immediately know what our normal vector is for this plane. Now, it's not hard to do a dot product with the E2 vector. Here's the E2 vector, 0, 1, 0. Easy dot product. And that dot product is very clearly 0. And that tells you that your normal vector here is perpendicular to the y-axis. And now I'm just going to make a geometric appeal. If the plane is perpendicular to the normal vector, and if the normal vector is perpendicular to the y-axis, again, geometric appeal, right? Think about what that sort of unavoidably would have to mean. The conclusion is that the plane must be parallel to the y-axis. So this plane here has to be parallel to the y-axis. So nice little freebie little result. Okay, is everybody okay with that? Everybody's happy? Right. Okay, next one. This next one is another little puzzle. We've already done sort of one of these lines and planes puzzles. Here, last time, we talked about finding the equation of a plane given 3 points that the plane contains. And again, there's kind of the puzzle aspect to it, and trying to connect the dots in some sense, however you can. So just another example of that kind of thing. And I like to start with this example with the idea that the first thing that I think you should do in questions like this is translate the given algebra and the goal algebra into given geometry and goal geometry. Right? So we were, as the question is stated, we're given 2 equations and we're looking for a parameterization. Let's not think of it in those terms. Let's think instead geometrically. Notice these equations tell me normal vectors right off the bat. So I'm given these vectors, these normal vectors. And what do I want? Well, let's see. I want a parameterization. The parameterization requires a starting vector that's given. I don't really need that. I already have that. So really, to get right down to it, what I really need is this direction vector parallel to my line. So this is what the question translates to geometrically. Don't think in terms of equation and equation given, look for a parameterization. Think of it as these vectors are given and this vector is sought. Does that make sense to everybody? We've kind of gotten the algebra out of the way. We're going to think geometrically because it's better for intuition. Okay. Now, with this observation having been made, how do I take a couple of given vectors and produce a vector parallel to the line that's parallel to the planes that these are perpendicular to? I know that's a mouthful, right? So what we want to do is ask geometrically, what can I see from the picture? What does my geometric intuition tell me is the relationship between these? And the vectors are perpendicular to the planes, which are parallel to the line, which is parallel to the vector. And I'm going to just say geometric appeal. That means that this vector needs to be perpendicular to both of these input vectors, both of these given green vectors. Does everybody buy that? Okay, so given a couple of vectors, I need to find another vector perpendicular to both. And of course, we recognize that cross product does that for us, right? So that's why we're going to compute our direction vector as N1 cross N2. And we win. Everybody happy with this example? All right. Now I want to warn y'all about what I like to call a little bit landmine. I just used two, what I'm going to call transitivity arguments. Let me explain what I mean by a transitivity argument. In this example that we just finished with, I argued that this vector, for example, is perpendicular to this plane. And then I argued that that plane is perpendicular to that vector. And so this is perpendicular to that, and that's parallel to this. Then transitively, in a sense, the original vector must be perpendicular to the final vector. Right? So this connects to that connects to the third, and then drawing a conclusion about the first and the third. So I'm calling that a transitivity argument. Let's look back at the previous example. There was a transitivity in there as well. The plane is perpendicular to the normal vector. The normal vector is perpendicular to the y-axis, and therefore the plane is perpendicular to the y-axis. Parallel to the y-axis. So again, a kind of a transitivity. So these kinds of transitivities, they come up a lot. It's very handy. It's just ubiquitous. It's geometric intuition that it's going to be all over the place in arguments that you'll make along these lines. And here's the nasty little thing to be aware of. Not all transitivities that look like they ought to be true actually are. So this is, like I say here, this is a warning. Okay, think very carefully and heads up. For example, notice this vector is parallel to that plane, and that plane is parallel to that vector. And it's tempting to make some sort of a connect the dots if this is parallel to that and that's parallel to the other. Wouldn't it seem that V and W ought to be parallel? But no, they're not. And not only are they not parallel, they're not anything. They don't have to be parallel. They don't have to be perpendicular. No relationship. So, heads up, be on the lookout for this kind of thing. Don't just assume that things that look good on paper are actually geometrically true. Here's another example. P and Q are perpendicular. Q and R are perpendicular, but P and R, no relationship. Now again, on paper, you look at P perpendicular to Q, Q perpendicular to R. It really seems like you should be able to make a case for something here about P and R. And you just can't. It just does not work. Okay, so fair warning. Now, all of this said, you are, of course, going to have to be making geometric appeal type arguments. I mean, of course, that's just unavoidable. So, on the one hand, I'm warning you about this. On the other hand, I can't enumerate a complete list of all valid transitivity arguments. There's too many different versions of lines and planes and which is perpendicular to what and what's parallel to what, and there's a bazillion different combinations of ways you could make candidate transitivity statements, And even if I could enumerate all of them, it wouldn't be reasonable for me to expect you all to memorize them, nor would I believe that you'd be able to retain a memorization of all of them for a useful amount of time. So the rule in this course is going to be, feel free to make any valid transitivity argument, right? So just make sure to double check your intuition, make sure that the transitivity argument you're making is actually true. And if it is, go ahead, no problem, all good. Does that make sense? Okay, moving along. How do we parameterize a plane? We've already talked about parameterizing a line. Parameterizing a plane is kind of the same thing, really. We start with a given point, and now I've got this whole great big plane. I need to figure out how to get from this given point to any other point in the plane. In other words, I need to be able to generate the entire plane. I need to be able to produce any point in the plane by starting with a given point. So the idea is then that if I know a couple of vectors parallel to the plane, notice that by going appropriately far in the v direction and then subsequently appropriately far in the w direction, I can produce, well, any point in the plane. Right, now how far do you need to go? Well, I don't know, it depends. It depends on where this point is, right? But just by choosing S appropriately, I can go as arbitrarily far, but S being negative would take me over that way, right? I can go as far as I need in the v direction, and likewise, then as far as I need in the w direction. And I can sweep out the entire plane. Is that cool? Everybody happy? Yep.
So before we had like just T, and for this it's like S and T.
That's right. That's right. That's a great observation. That here, let me get rid of the mess. The parameterization of the plane is kind of just an extension of a parameterization of a line. And arbitrarily, it doesn't really matter which one you use, as first or second. But yes, absolutely. Yep. Okay. All right. So example. Hopefully a familiar example. You may recall we've previously talked about this plane that contains three given points, A, B, C. And we talked about how to find the equation of this plane. Now we're going to find a parameterization of this plane. Let's see here. We previously talked about how you can subtract one from the other two to make vectors parallel to the plane. This was the point in that old example where we thought, well, we need a normal vector to make the equation, so how can we get a normal vector? And then we started talking about cross products and stuff and took it from there. Here, we're parameterizing. I don't need a normal vector. I just need two vectors parallel to the plane. I already have the two vectors parallel to the plane. We're actually kind of done, right? So all I have to do then is take any point I like of these three. I like this. Oh, whoopsie. I like this one arbitrarily because it has the smallest numbers. And then I have my two vectors parallel to the plane. S and T are my parameters. And again, we win. That parameterizes my plane. How are we doing? Is everybody happy? All right. Okay, so next we have a bunch of what I'm going to call distance problems. Various different geometric objects, and how do I compute the distance from the one to the other. Again, I'm not going to enumerate all possible versions of this, but I want to show you the key tricks, the key tools for your toolbox, and apply as appropriate as needed. So starting with, I'm going to say kind of the easiest one. Suppose you have a point given and a line given, and you want to find the distance from the point to the line. Now let's be careful about what do we mean by the distance from the point to the line. There are arguably a bunch of distances that start at the point and end on the line, right? I mean, so here's a bunch of such distances. Which one do I mean when I say the distance from a point to a line? And the rule is when we say the distance from something to something else, we always mean the shortest possible. Among all candidate distances, which one is the shortest? That's what we mean by the distance, right? So, for example, imagine that the line is the coastline and the point is you and you're offshore. If somebody asks you how far offshore were you, well, of course they mean perpendicular to the coast, right? That's understood. Does that make sense to everybody? Is everybody okay with that? Okay. All right. Okay, so how are we going to find that distance? Notice, by the way, we don't know this point, right? So it's tempting to say, well, just find this point here, and that's the distance, but that's not given. So what we have to do is kind of do a little bit of work to get there. I'm going to point out that I can subtract, do x minus x naught, right? For so any arbitrary point on the line to the point in question. That's not the distance that I'm interested in, but I can talk about its projection to that line. Very importantly, the projection, not the component. I need the vector, right? So you talk about that projection, and then check it out. W minus its projection gives you this vector that I'm going to call D. That vector, the whole idea of a projection is that this subtraction will give me a perpendicular vector. That perpendicular vector is the one whose magnitude is the distance. Everybody happy? Okay. All right. Now, let me show you a different way to proceed. Pros and cons. But I like it when there are arguments that use clever methods. And this is another example of a clever method. This is another mathematical bank shot. We're going to get to something we're interested in by thinking about something we're not interested in. Specifically, we're going to think about this area, which I emphasize, not the question, right? The question was to find the distance, D, that I have right there in the picture. Okay, so what I'm going to do is I'm going to take this thing that's not what I'm interested in, and I'm going to compute it two different ways, and then try to benefit from that. So on the one hand, area is height times base, high school geometry. On the other hand, area is magnitude of the cross product, assuming we're in 3 dimensions, of course. Now still, it remains, I don't actually care about the area, right? But because I've computed area two different ways, it follows that both of these things have to equal to each other. And again, not that I care about the area, but because those two things have to equal to each other, I can then solve for the distance that I'm actually interested in. That's a real cool trick. I've seen this in various different contexts at a variety of different levels. If you ever take a complex analysis class, there's a version of a trick kind of like this that can be used to compute an otherwise intractable interval. That's just kind of cool how this works out. So anyway, sometime, if the takeaway here, if you can involve the object that you're interested in a computation of something else that you don't actually care about, then you can connect that thing you're interested in to something else and foot in the door, and sometimes everything just comes together. So anyway, nice method, yeah.
Instead of calculating like the length of P with the projection, can you just do the length of W?
Well, no, because so when we're talking about this right here, so we're looking at this area, right? And we have to talk about height and base, right? So the base has to be perpendicular to the height. Yeah, so it's tragically it does have to be perpendicular that way, yeah. Okay. All right, here's another one. Suppose I have parallel planes. Like so. How do I find the distance between these parallel planes? Okay, well, it's another one of these. It's different, right? It's not like a point and a line. What are we going to do about this? Again, reminder, what do I mean by distance? I don't mean pick any point in the one plane, pick any point in the other plane, right? I mean, what's the shortest possible? In this case, what is the perpendicular distance between these two planes? So the way to do this one, and again, this is just tools for your toolbox, start by picking any 2 points. They probably won't be the right points, right? They probably will not create a perpendicular vector. So it's probably not what you want, but that vector, if you look at its component in the normal direction, you think about, reminder, what is a component? Right? And a component says I want the part, forget about the part that's perpendicular to my in vector, I want just the part that's parallel to my in vector. And notice that component then is the distance that we're looking for. I'm sorry?
What's the n vector?
It's the normal vector for these planes, so keep in mind they're parallel, and so that means they have the same normal vector. Yeah?
Why is it the parallel component bigger than the same?
Why the what now?
Is it you said it's the parallel component bigger than the same?
Well, it's the part parallel to the perpendicular vector.
Okay.
Right. So that's right. This component is parallel to the in vector, and therefore it's the part of light blue that is perpendicular to the plane. Yep. Okay. Now there is one little asterisk on here, and as I've said before and done before, I like to first say it the intuitively satisfying way, and then come clean up, mistakes and messes after the fact. So I said that distance is a component, but it's not. Distance is an intrinsically positive thing. Unavoidably, it has to be positive. Component is a coordinate. It's a scalar. It doesn't have to be positive. And so, for example, if I had arbitrarily, when I wrote down this normal vector, if I had written it the other way, if I had written the normal vector like so, right, then the component of that vector in that downward normal direction would be negative. Distance is positive, though. So anyway, no big deal. The way we fix this is just by recognizing that component has a plus or minus that we don't care about. And so take the absolute value. Throw away that whole plus minus nonsense that we don't want. Problem solved. Okay. All righty. Last one. How do you find the distance between two skew lines? So like so. And make sure to be clear on what skew means. Skew means that they're not parallel and they don't intersect. So skew means that these lines have nothing in common. They don't share a point. They don't share a direction. They're just unrelated lines. Okay. How would we compute the distance there? Now, this is arguably, at first glance, seemingly a really hard problem, because on the one hand, I could pick, a point on one of the lines, and I could look at all the different possible distances to the other line, and I could talk about which one of those is the shortest, right? But how do I know that I picked the correct point in the first place? And if this is the shortest of the distances I was just looking at, how do I know that that is the shortest of these? Right? Maybe it isn't. Right? So don't forget that there are, you have to look at all possible distances and see which is the shortest of all possible distances among all points on L1 and among all points on L2. Right? So it's kind of a two-dimensional problem. So it's tricky. Here's the foot in the door. Beautiful observation. If you have two skew lines, I claim you can always put those two skew lines inside of parallel planes. You can always do that. It seems a little too good to be true, right? The whole point of skew is that the lines have nothing in common. So how can I just assert that there will always be a pair of parallel planes that does this? Well, here's the idea. Take the original two lines. Look at these direction vectors. Right? Take those two direction vectors and cross them. This produces what I'm going to call a normal vector. This normal vector is perpendicular to V1. It's perpendicular to V2. Therefore, this normal vector is perpendicular to L1, and it's perpendicular to L2. Right? Therefore, this plane, or I'll say these planes, all of these planes that I can generate within, they're all parallel to L1 and L2. And so to produce the relevant planes, all you have to do is, so for example, for L2, just pick some point on L2 and use that as your x naught. Boom. Now you've got an x naught and a normal vector plane. And likewise, pick some point on L1. Doesn't matter which one. That x naught and your normal vector produces that plane. So you can always put skew lines into parallel planes. Now, who cares? Well, this was not the question, right? The question was to find the distance between the skew lines. And the wonderful observation here is that the distance between the skew lines, perpendicular in both directions, of course, that distance between the skew lines is also the distance between these two parallel planes. Again, perpendicular on both sides. And the distance between parallel planes, we already know how to do. So this is another classic problem-solving technique in math, by the way, is take a question that you're trying to solve, turn it into a question you already know the answer to. All right. Yes?
Are skew lines, like, finite?
No. They're infinite. Yeah, I can't draw them infinitely long. Yeah.
So, but if they're not parallel, and they don't intersect.
Like this.
But wouldn't those have to be parallel to not intersect?
No. These, my left hand and my right hand, not parallel, right? Okay. Parallel would be like this. These are not parallel, and yet they don't intersect. No? So this is in 3 dimensions, to be clear. Right? In 2 dimensions, not parallel lines have to intersect because there's just no space. They can't avoid each other. That's trains on, if the tracks cross, then the trains crash, right? But in 3 dimensions, like just like I have my arms here, these don't intersect, but they're also not parallel. Is that satisfying?
Yeah.
It just, you kind of gotta think it through, but yeah.
But then they're on parallel planes.
Yes.
Okay.
Yeah, that's right. Yeah, a little counterintuitive. Yeah. Yes.
It's kind of on the same thing. So that's like the difference between the 3D and the 2D. Is if you moved up the planes that they were touching, they wouldn't.
Say it one more time.
If we move the 2 planes, which is like the 3rd dimension, then they wouldn't intersect.
Move. I guess I'm not following the.
I guess the reason why the planes. I'm just trying to understand as well because I'm struggling with it.
Okay.
The reason why the planes have to be parallel is because if they weren't, it actually would intersect in 3 dimensions.
It's not that they have to be parallel. It's that I mean, I could put these lines into a bunch of different planes, right? And I don't care about other kinds of planes. I'm just saying I can always put these 2 lines into parallel planes. These are the only planes I'm going to care about. Now you're right. There's a bunch of different planes that contain this line. I just don't care about those planes. So does that make sense?
I think so.
Okay. Yeah. Okay. All right. So clever little trick there. And let's see, I believe that does it for 1.5, and we're moving on now to 1.7. So some new coordinate systems. Y'all are already familiar, I presume, with rectangular coordinates. X and Y coordinates, for example, in R2. Nothing to it. Very familiar. A couple of neat facts about rectangular coordinates that are worth appreciating. For every point in R2, there is exactly one X coordinate. Right? If I give you some point in R2, it can't have multiple X coordinates. That's a bunch of nonsense. No way. There's exactly one X coordinate. There's exactly one Y coordinate. And so for every point, there is a unique set of coordinates for that point. And it seems like a triviality to say, right? Why are we bothering, observing things that are perfectly obvious? And the reason is because, sadly, when we switch to different coordinate systems, like in a couple of seconds here, we're going to start talking about polar coordinates. Polar coordinates does not have this property. So we have to say farewell to this idea of uniqueness of coordinates. We're not going to be able to have that convenience in polar. Likewise, here's a really good one. The rectangular coordinates are also coefficients in a linear combination of standard basis vectors that produces that point. Handy, right? By the way, arguably kind of a definition of coordinates in some sense, right? I hope you all remember from linear algebra class that if you have a basis, then the coefficients in that linear combination that produces a given vector are the definitions of the coordinates. Anyway, first, in this context, I'm going to call this a kind of a perk of rectangular coordinates. And that's arguably a special case of this more general statement about how you do linear combinations of vectors. If you do a linear combination of vectors, whatever the coefficients are in that linear combination, you're going to do the same linear combinations to the individual coordinates. Again, handy, super nice algebraically. Y'all have used this fact a bazillion times in linear algebra classes and maybe even other contexts. Okay, so again, we'll of course, and again, don't get used to it because there is no version of this in polar coordinates or cylindrical or spherical, any of the other coordinates we're going to use in this class. Okay, so again, say goodbye to those. Okay, new coordinate system. We're going to talk about polar coordinates. I think a lot of y'all have probably seen this before. I'm going to present this a little bit differently. I think importantly, differently than how you might have seen it before. I like to think of polar coordinates as relating to a function. There is a function that says if you give me these things called polar coordinates, which you can think of as an ordered pair, r and theta, that input produces then an output, which is a point in the xy plane. So we have coordinates that are the inputs that go into a function that then spits out the corresponding point. Okay. So now how does this work? I mean, given a set of coordinates, how do I produce said point? The idea is that the theta, what we call the theta coordinate, tells me a direction. The way I get that direction is by starting with the positive part of the x-axis and rotating counterclockwise until that defines a direction like so. Right? And then r, let's see here, color choices. R is, again, let me clean this up later. R tells me how far to go in that direction. So if R tells me to go that far in that direction, then that produces this point right there. Everybody on board? Is that cool? Just out of curiosity, how many people have seen this before in some version or another? Okay, good. All right. Okay, now to be clear, I did commit a little math crime there. Let me fix that. I noticed the air quotes right here. How far? That makes it sound like I'm talking about a distance. distances are positive. R is a coordinate. R does not have to be positive. So when I say how far, that's sweeping under the rug the fact that R is perfectly entitled to be negative. There is not a thing at all wrong with R being negative. If R is negative, no big deal. Just instead of going that way, just go the other way. Right? You can think of it this way instead. Let me clean up my picture a little bit. Think of it as that you have what you might think of as an R-axis defined by the angle theta, and that being the R-axis, maybe that's where R equals 2, and then maybe this is where R equals 1, and then this is where R equals 0, and so no surprise that that is where R equals -1, etc., etc. It's as if there's an R-axis there like that. Does that make sense to everybody? Okay. All right. Okay, let's see here. Let me do like that. Get rid of all of that. Okay. Okay. So now, what are the details here? Given an R and a theta, how do I find the corresponding x and y? And this comes from a given point. You can just draw this corresponding right triangle. And now I'm going to wave my hands at y'all's existing proficiency with geometry and trigonometry and all that stuff from high school. Looking at that triangle, you can persuade yourself that x is our cosine theta and y is our sine theta. So make sure you're good with your trig and that this is comfortable. And by the way, with all of this, I'll constantly be making references to prerequisite blah blah blah. And if you find you are uncomfortable with some of that stuff, then that's something that you're going to want to solidify. So the internet's full of references and stuff like that. And if you get stuck on some point that I've referred to as being a prerequisite, you're very welcome to come to office hours. Right? I'll be happy to show you the basics of it and point you in the right direction. Okay, so we've got ourselves a coordinate system. First observation to make, though, not unique. So, tempting to think it'd be unique because if I have a point, then, there's a direction that I go from the origin to get to that point. Right? And so doesn't that just tell me what my theta is? And then, of course, there is a how far. Oh, gosh, that's terrible. There is a how far that tells me how far to go in that direction to get to the point that I want to get to. There's your theta. There's your r. How is this not unique? And the failure of uniqueness, one failure of uniqueness is to notice that if I were to add 2 pi to my angle, that just gets me going to exactly the same direction. Right? So this angle that what I first drew as my green angle theta looks like it's about pi over 4 or so, right? But if I add 2 pi to that and give myself, 9 pi over 4, it's still going the same direction in the xy plane. And yet it's a different angle, right? That theta plus 2 pi is not the same angle as theta. Does that make sense to everybody? That's kind of annoying. And by the way, you're not limited to just going around 1 extra full turn. You could go 2 full turns or 17 full turns, whatever. Right? Any multiple of 2 pi. And it's worse than that because look at this as well. Let's see, let me just clean up all of this. Again, given this angle theta. What if I just went an extra 1 pi? Just an extra pi, that would get me going exactly the wrong direction. Again, so, an extra half turn, exactly the wrong direction. Now, you're tempting to say, okay, well, that's a swing and a miss. I can't get to the right point by going the wrong direction, right? But keep in mind, R is allowed to be negative. And if I go exactly the wrong direction, a negative amount, there we are, back to that same point, right? So let's see here, this negative value of R gives you polar coordinates that also still go to the same point. Does that make sense to everybody? That's a little bit annoying. Okay. All right. Watch out for clarity problems. We have multiple coordinate systems in play now, right? And that being the case, when you write down an ordered pair, it is not immediately obvious from having written down an ordered pair what coordinate system is this assuming, right? Are these the rectangular coordinates of a point that I'm talking about? Or maybe these are the polar coordinates of a point that I'm talking about. Now, a lot of students will look at this right here, pi over 6, and say, hey, come on, that's an angle. Right? Surely pi over 6 is an angle. And if pi over 6 is an angle, then that means that this is the R, and that means that surely we're talking about this point right here. You'd think, right? But okay, that's probably even true. But 2 is still a perfectly reasonable candidate that could be X. And pi over 6 is still, it's a perfectly reasonable real number. This could totally be Y. I could, by what's written there, totally be referring to 2 comma pi over 6 in rectangular coordinates. That could be this point right there. And it's from what's written here, not at all clear which of these points is being referred to. So, heads up. And now sometimes the context will make it clear, but if it's not, I strongly encourage you to clarify. So, for example, look how easy it is to just write something like this. R comma theta equals 2 comma pi over 6. Ambiguity gone. This very clearly makes it the case that I am talking about the polar coordinates, and so I mean that, not that. No problem. So easily fixed. Everybody happy with that? All right. Okay, here's another kind of polar coordinates landmine. A lot of students get this wrong. A little bit of easy geometry allows you to write down these equations. Right? We have kind of a Pythagorean relationship between x, y, and r, and the definition of tangent gives you y over x. Again, not too much trouble to do the geometry on that. And students have this urge, a lot of students anyway have a strong urge to solve for r and write r equals square root of x squared plus y squared. And to solve for theta as, arctan of y over x. And I'm writing those down here, and you're welcome to write them down too, but notice that the very first thing I'm going to do is I'm going to cross them out, because those formulas are not always true. AKA, they're not true. So now, how do I know these formulas? Well, what do you mean these are not true? Let's take these one at a time. This one here, r equals square root of x squared plus y squared. The devil's in the details. This symbol right here, the square root symbol. Got to be very, very careful as to what this symbol means. This symbol does not mean whichever square root you feel like. It also does not mean both of the square roots of the number under the radical. This symbol means the positive square root. That's what this means. So if you claim r equals the square root of x squared plus y squared, you are claiming that r has to be positive. That is not true. R can totally be negative. Sometimes r needs to be negative. So this formula is just not true. Likewise, this formula right here, arctan takes very limited set of values. Right? Arctan is always between negative pi over 2 and pi over 2. Theta is not constrained to always be between negative pi over 2 and pi over 2. It just isn't. Right? So this as well, not true. So heads up on that. It's real easy to be sloppy on that point. By the way, it's worse than what I've presented here. A lot of students at this point in the lecture tend to think to themselves, okay, fine, well, I'll just use these equations to get my first set of polar coordinates. And then I can always add pi and make the r negative and, stuff like that. That doesn't work either. So let me show you the example of that crashing and burning. Let's think about this point right here. -1, -1. Here it is. It's in the third quadrant down there. And let's try to write down the polar coordinates. And if you were to just take these formulas, which again, please don't. If you were, though, to just take the positive r and the arctan value of theta, then you would get these values right here for r and theta, which gives you that point right there, which is wrong. It's not even that weird of an example, right? I mean, this is not some obscure, tricky point that, where this is some sort of anomalous counterexample. This is our easiest point in the third quadrant, right? And these formulas fail and give you a totally wrong point. Does that make sense to everybody? So don't trust them, right? So now I'm going to cross these out, never to uncross them again. That's a bunch of nonsense in multiple ways, right? So the way you're actually going to solve problems like this is, let me just go ahead and erase them. The way you're actually going to solve problems like this is to look at these formulas that I started with, right? See what r squared has to be. See what tan theta has to be. See, therefore, what your corresponding options are for r and theta. And at this point, use geometry. Let your geometric intuition answer these questions for you, right? So, for example, looking at pi over 4 as my angle. Looking at the picture, right? Here's my actual point. This is what the angle pi over 4 does. How far should I go in this blue direction? How far, air quotes, should I go in the blue direction to get to the purple point? Well, obviously I have to go backwards. So pi over 4 pairs up with the negative r option, not the positive one. And again, the picture just is what resolves that for me. Right? Just geometric intuition. Likewise, now let's look at, let's see here. Well, I guess I'll do it like this. Let's look at the 5 pi over 4 candidate, right? So that would be that angle. So in this dark blue direction, how far do I need to go in the dark blue direction to get to the purple point? Well, in that direction, the point is in that direction. So a positive amount in that direction. So the 5 pi over 4 pairs up with the positive r. Does that make sense? All right, so again, heads up, be careful. Oh, and let's see, how are we doing on time here? We have less than a minute left. I tell you what, let's call it a day. I probably owe you all time anyway, so we'll quit right there. One last little super quick thing. I just want to. I'm going to send y'all an email tomorrow, formally announcing we are beginning to check class attendance starting on Wednesday. The class roster should be completely settled by then. And so anyway, don't forget attendance does count as part of your grade, blah, blah, blah. I'll be starting to call names and stuff before class actually starts. I'll be using that as a tool for learning names, which usually takes me a half a semester because there's so many of you. I'll have like 120 students this semester. So eventually I'll get there. But anyway, starting on Wednesday, see you then.